the aim, that is to be the estimation of the power spectral density of the input discrete time random process by using the Welch's technique here. So as like the previous cases we have done, we shall first of all develop a function which will have the input of the discrete time random process and few other parameters that are required for the processing of the Welch's method, and it will provide us the output of the power spectral estimation by the Welch's method here. So we expect it to be developed as a function, hence we write the keyword function, and the function is supposed to give us the output as power spectral density. So we write capital P small x as the output variable. The name of the function here we provide it as Welch, and the input here we provide, of course, the x as the discrete time random process, comma we require capital L. So as we have seen in the case of Bartlett's method also, for the periodogram averaging, thereupon we had the subsequences formed from the original discrete time random sequence thereupon. So L will be holding the length of the subsequences here, comma as we have seen that the Welch method is essential modification from the earlier Bartlett's method where the overlappings have got involved. We require one variable to hold the information of overlap, the amount of overlap, and that we can designate with the name overlap here. Next to the overlap, we require the last variable. So in the Welch method, instead of the use of the periodogram method for averaging purpose, here it is the use of modified periodogram, the second method into the category of non-parametric approach. Hence, for the modified periodogram, the use of the windows for the application to the discrete time sequences are there. Therefore, the 5 alternatives of windows that we have seen into the demonstration of the modified periodogram, we require the variable with the name window. So it will be giving us the type of the window that can be used for operating the given signal for estimation of power spectral density. So here, as into the periodogram, we required only the 3 inputs x, n1 and n2. The modified periodogram required the window as one more parameter, the 4 parameters here. The Bartlett's method we have seen with only the 2 input parameters, the how many number of subsections we want and the input discrete time random process. Here we require the input discrete time random process x, then we take L, the length of the subsequences, the amount of overlapping between the subsequences, and the type of the window that we can apply for the calculation of the modified periodograms here. So this is the syntax of the function, and to develop the body of the function, at the last we use the keyword end here, and in between these two keywords function end, here we have to develop the function for the application of the Welch's method here. So we first of all save this into the same folder by the name Welch here. The function name and the file name with which we save it should be the same here. Now we specify very first of all the input parameters. X is the input sequence, L to be the section length, subsection length basically, over to be the overlap amount here, and the value should be in between 0 to 1. So it should be greater than 0 and it should be less than 1. Whereas the types of the window as we had described earlier, here we take window that is to hold the value. Suppose it holds the value 1. So this is nothing but the conventional rectangular window. Next to that, if we go for the use of the 2, so it is supposed to work with the Hamming window. After this, we are supposed to make the use of the third option where it is Hamming window. Next to that, we have the fourth option where the window type is nothing but the Bartlett, and the last one is the fifth option here, and this fifth option, it is supposed to work with the black one type of the window here. Now with respect to the number of input arguments, here we can use the if statements. So we write first of all if, and the condition here it is if nargin. Here we have if it is having the 3 input arguments, so that time we assign the variable name, that is window. So window type should be the one here. We end this if statement. Next to that we take the another case, and yes, of course, if the number of input arguments not only equal to 3, but it should be less than or equal to 3 here. So that time we can go for the use of window is equal to 1 here. Now further we have the condition for the input arguments. We provide the condition nargin to be less than or equal to 2. So in that case we take the variable to hold the amount of overlapping, that is the overlap, with the declaration of the value initiated at 0 here. We end this statement as well. Next to that we put the condition if. Here we have nargin only one input variable if it is there, so that time here we assign the entire length here of the input discrete time random process denoted by x here. So here we write length of x, and that is assigned to capital L here, and that it will be the entire discrete time random sequence here. So there won't be any kind of the subsections here, subsequences here. Now after this we can have the another condition with which we can proceed, as this Welchs method involves the amount of overlapping here. So for that purpose we have if command, where we have the variable overlap, that is greater than or equal to 1, and along with we have the condition that this overlap is less than 0. So in that situation we have to put the error displayed onto the command prompt here, and the error, it will be within the pair of parentheses and a pair of single quotes. The amount of overlap is invalid. We end this condition also for the if statement. Now we begins to start for the range of the discrete time random process signal here, sequence here, to be started at n1. So that is equal to the first sample, we write the value to be 1, and n2, that it is the ending index. n1 we can call to be the start index, n2 we can call to be the ending index, and that it will be equal to capital L here. So the total entire length of the subsequence here. Now along with n1 and n2 we require the another variable to be defined here, that is equal to n0, and this n0 is assigned the value 1 minus the amount of overlap, that it is the variable, multiplied by the entire length of the subsequence, that it is capital L here. Now with this much of knowledge we can have the definition of the variable, that how many number of the subsequences to be formed here. So for that purpose we have the variable with the name n sub seq, n subsequences here, and this we can define as added to the MATLAB syntax floor operated over, here we have within the parenthesis the entire length of the discrete time random sequence x minus the length of the subsequence capital L, which is divided by the variable that just now we have defined in the above step, that it is n0. We end this index with the help of semicolon, and now as we are supposed to use the for loop for the estimation of the power spectral density, initially we define and declare that particular variable to be with the value 0. So capital P small x, the power spectral density estimate, we initially assume to be equal to 0. So as it will be priorly declared this way, it will be having the fast computation in this particular programming. Now it's time to have the application of the for looping. Here we make the use of index variable to be the I, and that can hold the values into the iterations right from 1 up to the variable having the number of subsequence lengths here. So n sub seq here that we have defined in the above step here. So for these many times of iterations here, now the output variable capital P small x can be computed, where initially it is equal to 0 and it will be added with. Now as we have to make the use of modified periodogram for the case of the Welchs method as a modification from the Bartlett's method here, now we have to call the function that we have developed into one of our previous topic, that it is the sixth video of this chapter for the demonstration of the modified periodogram. Here it is available into the current directory that we can call here. So here we have to write modified underscore periodogram, and to this particular function we have to provide the input x as the input discrete time random process, window as the function, input another one, the 5 tops of the window we can operate with it, n1 the starting index of the discrete time sequence, n2 the ending index of the discrete time sequence, and this is divided by the number of subsequences here. So n sub seq here we end it with the help of semicolon. Next to that we compute n1 is equal to, here we write n1 added by the variable n0. In the similar fashion, the n2 can also be incremented by the earlier n2 added to that of the variable n0 at this stage here. Now it's time to end this particular for loop here. So we end it, and now we have to save the changes to the script of the Welchs function here. So here it is the Welchs function generated into the current folder, as well as we have the name onto the editor tab. Now we have to call this Welchs function and operate it onto the discrete time random process. So for that purpose we have to generate that random process, and here we take the another MATLAB script here where we can have generation of such the discrete time random process here. So we begin by mentioning close all, clear CLC to start the fresh execution of this particular program. The first module here we make to generate the discrete time random process. Discrete time random process we have always been denoting by the variable x of n here in the mathematics. Here we make the use of variable x only here. So as the various ways we have seen for the generation of the discrete time random process here, the two ways here we shall mostly be opting here. The first way is to directly assign the various values to the selected number of the samples that you want it to have. So for example, I start with minus 0.7 one sample, here it is, another sample 3.4, the third sample 4.5, fifth sample minus 8.2, sixth sample, here it is the 6.2, seventh sample 4.5 again, eighth sample, here I make minus 3.4. next to that we can take here the 21 as the value, or we can reduce it to the value 2.5 for example, and last value we can take 6.7 here. So here we have three values to this, 1 2 3 4 5 6 7 8 9 values we have. The last one value, for example, let us take 5 here. So this way we have assigned the values to the x here, and now let us see what we have generated here, that is visualized graphically with the help of the function stem here. And now we have to also save this function to the current directory, that we can name it as execute underscore, here we write Welch. So saving it, and as we execute this particular program in the workspace, we can see here it is the variable x generated with the values that we have assigned in this particular MATLAB statement here. Along with, because of the stem function that has been executed here, we have obtained this figure, and it holds the samples right from 1 to 10 as you can see onto the horizontal axis. Here we have the different amplitudes. The first sample here we have that holds the amplitude minus 0.7, the second that holds 3.4, third holds 4.5, fifth holds, fourth holds minus 8.2, the fifth one 6.2, sixth one 4.5, seventh one minus 3.4, the next that it is eighth one 2.5 the amplitude, ninth sample holds the amplitude 6.7, and the 10th sample holds the amplitude 5 here. So these are the various amplitude levels into the random form for the discrete time sequence here. So this window we close. The first module is completed, that we have generated the discrete time random process, and now we can have the application of the developed Welch function to such an input here. So now here we take the another module and write the comment that to estimate the power spectral density here, and this is of course by the use of the Welch's function here. So for the same we have to call upon the Welch function that we have developed here. So we expect the output to be holded by the variable capital P small x, and here we write the function name Welch. As the inputs here we can see into the syntax, we require the value of x, so x as a parameter variable here, value of L we require, value of overlap we require, and the value of window we require. So depending on that value, whether it is 1 to 5, so these are the various windows that we can make the use in this processing here. So now to this Welch function we provide the input discrete time random process x equal to the one that we have developed here. Next to that, the next parameter is equal to L here. So for the value of L we can select 5. Next to that, for the value of the overlap variable, the overlapping here we can select 0.4 overlapping, and lastly the window type has been asked for. So let us select for example the window number 4, the Bartlett case here. So with these input arguments we end this syntax with the help of semicolon. So let us run this particular program whether the variable px is generated into the workspace along with this x or not. So here when we write the function Welch having the input parameters x. Next to that we have the values 5, 0.4 and then 2 for the window selected here. Now let us see, after saving the changes, if we execute this program, whether the px variable generates to the workspace or not. Here we can see onto the workspace px has been generated with the size, the dimension here 1024 by 1 of the type double here. As well we have this first window to display the input discrete time random sequence here. Now here we can have the third task, that is to have plotting of the function here. So we write to plot the spectrum estimation here, spectrum estimation, or simply the spectrum estimate here. So for plotting purpose we can make the use of simple plot function. If we require the separate window, we use the keyword figure, and to this plot function we can provide the input as the variable px here. So upon saving changes, as we run this particular program, here we can see into the figure 1, here we have the display of input discrete time random process having the 10 samples, whereas into the figure 2 we have the plot of the power spectral estimate here. So this way we can have the maximization of this particular window. So we can have total 1024 samples here. So this is the value and the amplitude achieved into the frequency domain, that it is 11.4 here. So the two peaks you can visualize for this particular discrete time input random process here. The another way is to have plotting of the spectral estimate into the terms of decibels here. So for that purpose we make the use of figure again. Next to that the use of plot command, and inside the plot command we don't put directly the px here, whereas 10 in multiplication to the log to the base 10 computed over capital P small x here. So upon saving changes and running this particular program, we can see again the figure 1 as the discrete sequence and the figure 2 here in terms of the decibel values plotted onto the vertical axis here. Now along with this we have the another technique also, where the horizontal axis holds the values of the frequency in terms of the hertz here. So for that purpose we have to make the use of figure, then we have to again make the use of plot, where the input parameters are f, x here. So in that regard we have to define here the variable f for the frequency. So in general we can take the use of f defined as, let us say for example 4 in multiplication 2, here we have within the parenthesis the range is 0 to 1023, the entire range divided by 1024 samples here. So having the semicolon to end this particular syntax. So in the plot function, here we require the another parameter to be px instead of x, that it is the probability spectral density. So having the estimate of the power spectrum estimation, the px here. Now executing this particular m file here, we obtain into the first window the discrete time random process, and here it is the plot of the power spectrum estimation, and here you can see onto the horizontal axis the ranges, those have been marked at the intervals of half, 0.5, right from 0 to 4 here. So this we have taken for the random process having the 10 samples defined in this syntax. Instead of this, as like the previous cases, if we define x to be with the function randn, whereas the input variables are 1, 100. So at that particular point, if we go for plot of this particular spectral estimate, we get the output like this. So here it is the window, the output window, and here it is the input window. In the figure 1 we have the discrete time random process generated by the use of the function RANDN, and it is having the length 100 as you can see onto the horizontal axis at the intervals of 10 samples here. The first sample holds the amplitude 0.2696 here. The second sample holds the amplitude 0.4943 here. The third sample holds the amplitude minus 1.483 here. So this way we have this random process, and with respect to the plot by using the frequency in terms of hertz, we have this spectral estimate. Instead, if we make the use of only the plot of the spectral estimate having the decibel values here plotted onto the vertical axis, so we obtain such a plot. Here we have the decibel values of the magnitude plotted. At max, this graph extends to 0.54 value onto the positive side, whereas onto the negative side we have -1 decibel here. So this completes our simple MATLAB demonstration with respect to the Welch method of power spectrum estimation belonging to non-parametric approach here.